Okay, the next topic, H1 NMR spectra of metal carbonyl hydrates. H1 NMR spectra of metal carbonyl hydrate. In H1 NMR spectra, you know the chemical shift delta. Chemical shift. This is the delta scale. Delta scale. At 0, TMS is there. TMS, which is the reference. And here 0 to plus 12. This is the normal range. And this is the minus value. Minus value. Okay, delta in the units of parts per million. Normally, a shielded proton, highly shielded proton, lies in this region. Low delta. Highly shielded proton having low delta value. Shielded means surrounding that proton high electron density is there. Okay, surrounding the proton high electron density is there, so it is very shielded. A shielded proton having very low delta value, that is in the range of 0 and negative values. 0 and negative values, shielded proton, low delta value. If the proton is de-shielded proton, de-shielded proton, it is having high delta value. Generally, you know, carboxylic acid having the value, carboxylic acid having the value 11 and 12, in the range of 11, 12. Because the proton in RCOOH is very de-shielded. Because oxygen is an electron withdrawing group that will withdraw the electron density surrounding hydrogen. So the hydrogen, the proton in carboxylic acid is very de-shielded. So de-shielded having high delta value. At the same time, if the proton is surrounded by electron density shielded, it is having low delta. So we are discussing about metal carbonyl hydride. Okay, in metal carbonyl hydride, the proton surrounded by high electron density of metal. Okay, so it is highly shielded and having very low delta value, in the range 0 to minus 71 ppm. This is the range. 0 to why from 0 to minus 71 ppm, minus 71 ppm? Because in metal carbonyl hydride, for example, HMnCO 5 times. Here a proton is there. Then HTCCO5 or HReCO5. My question, what is the H1 NMR chemical shift of that protons? In HMnCO5 there is a proton is there. In HTCCO5 a proton is there. In HReCO5 there is a proton. What is the chemical shift of that proton? Because that proton is directly attached to the metal. You know, metal containing high electron density. So definitely that proton is highly shielded proton. Highly shielded proton means that proton having very low delta value. Okay, that is in metal carbonyl hydride, the proton surrounded by high electron density of metal, so it is highly shielded and very low delta value. What is the range of delta value? 0 to minus 71 ppm. Please copy this note. As shielding increases, it will goes to minus 10, minus 20, minus 30, minus 40, up to minus 70. Okay, as shielding increases, go towards the more negative delta. Shielding increases, more negative delta, minus 10, 20, 30, etc. Okay, so write a question. Question: arrange in the order of delta H. Delta H means H1 NMR chemical shift of the following complexes. You have to arrange in the order of delta value. First one, H, Mn, CO 5 times. Second one, H, Re, CO 5 times. Sorry, Tc, manganese, technetium, rhenium. Tc, CO 5 times. Then H, Re, CO 5 times. Which one having highest delta value? I arrange in the order of chemical shift delta value. Okay, you know all these protons are in a shielded environment of metal. Here, delta value explained on the basis of bond length. Okay, you know manganese is a 3D metal, technetium 4D metal, rhenium 5D metal. Okay, in manganese back donation is very high, size very low, so the manganese hydrogen bond length is very low due to high back donation as well as small size. Manganese is a very small sized element, so definitely Mn manganese hydrogen bond length very low, but technetium hydrogen bond length little bit higher and rhenium hydrogen bond length very high. For a comparison, I am representing in this fashion. Okay, so you know this manganese containing electron density. Similarly, technetium also containing electron density. Rhenium also containing electron density. So which proton will be in more shielded environment? Here manganese hydrogen bond length very low, so that hydrogen is very near to the electron density, so this hydrogen is very shielded. Okay, so bond length very low, and highly shielded. Okay, here comparatively high bond length high, and less shielded. Bond length high and less shielded. So what is the order of delta value? That means negative delta value. Delta value always from 0 to negative. Which one is more shielded? Higher the negative delta. Suppose this is 1, 2, 3. First case is more shielded proton. Means more negative delta value. So negative delta of 1 greater than 2 greater than 3. Negative delta of 1 greater than 2 greater than 3. Suppose for the first complexes it will be minus 30, then it will be only minus 20, then it will be minus 10. So negative delta, negative 30, negative 20, negative 10. Negative delta highest for first complex, because it is more shielded. Once again I am explaining, 3 complexes are there. In all the 3 complexes a hydrogen is there. Okay, my question, what is the order of the delta value? Normally metal carbonyl hydride, delta value of metal carbonyl hydride is 0 to minus 71 ppm, that is the range. So here it is explained on the basis of bond length. You know, a 3D metal and hydrogen, 5D metal and hydrogen. So this bond length is very shorter, means hydrogen is very in the environment of electron density. Okay, so very highly shielded proton and having very high negative delta value. This is poor shielding comparatively third one. Okay, so that is or you can generalize that the negative value of delta is inversely proportional to size of metal. That is a generalization. Okay, when size of metal decreases, negative delta increases. Manganese having low size compared to rhenium. When size of metal decreases, negative delta increases. Okay, so this is also a generalization. Okay, write the next question. So this is explained on the basis of size of metal and bond length. Smaller the size of the metal, smaller is the bond length. Okay, next question. First one, H, Mn, CO5, then H2FeCO4, H2FeCO4, third one HCOCO4, HCOCO4. Manganese, iron, cobalt, they belongs to same period, 3D series element. As you know, from left to right, what happens? Size of metal decreases. Size of metal decreases. When size of metal decreases, what happens? Metal hydrogen bond length decreases. When size of metal decreases, negative delta increases. Negative delta increases. So which one having higher delta value? Which one having higher negative delta value? Higher negative delta value. 3 greater than 2 greater than 1. That is the answer. 3 greater than 2 greater than 1. Why here cobalt having small size? Cobalt hydrogen bond length very low, highly shielded, very high negative delta value. And suppose for example its value is minus 7 point, exact value minus 7.5 ppm, and for this minus 11 ppm. Let's have a comparison. 2 greater than 1. For 2 minus, this negative only indicate shielded. The significance of negative is only shielded. Any other mathematical meaning. So minus 11 ppm, minus, this is minus 7 point ppm. Sorry, minus 7 point ppm. 7.5. Okay, which one having higher? 2 greater than. So 2 is more shielded. The significance of negative is it is more shielded. Okay. Okay, then next question. Third question. HF, CP, chlorine, hydrogen. My question, its a delta value equal to positive or negative? That is my question. Its a delta value is positive or negative? Fine. Hafnium, which group? Hafnium. സ്കാൻഡി ഇട്രിയം ലന്താനം ടൈറ്റാനിയം സിർക്കോണിയം ഹാഫ്നിയം. ഫോർത്ത് ഗ്രൂപ്പ് ടൈറ്റാനിയം ഗ്രൂപ്പ്, ടൈറ്റാനിയം സിർക്കോണിയം ഹാഫ്നിയം. ഗ്രൂപ്പ് നമ്പർ 4. ഗ്രൂപ്പ് നമ്പർ 4 മീൻസ് ഇലക്ട്രോൺ കൗണ്ട് 4. S2D4, S2D2, S2D2. Group number 4. Delta value positive or negative. You know, charge of chlorine -1, hydride H minus, Cp minus, Cp minus. So hafnium plus 4. Hafnium is group number 4. Hafnium plus 4 means its electronic configuration is D0. D0 means there is no d electrons. In metal there is no d electron. If metal actually the delta value is negative due to the shielding effect of d electron. Okay, but here the metal having no d electron, so it is definitely positive value, d shielded region. Okay, so in the case of D0 and D10, delta value is positive. In the case of D0, and if the metal is D0 or the metal is D10, in the case of D10 there is no paramagnetic electron. Okay, I heard about paramagnetic anisotropic effect and such thing. In D10 there is no paramagnetic electron, all are paired. That's the reason. D0 and D10 delta value is positive. So definitely in this complex, it is actually a metal hydride, but it's a delta value positive. Then another question number 4. Please write the question. CO4, a metal M, 2 hydrogen. Okay, follows 18 electron rule. Follows 18 electron rule if choose the correct option. Option A, metal, if metal equal to iron and delta hydrogen equal to 7.5 ppm. 7.5 ppm. Okay, option B, metal equal to tungsten and delta hydrogen equal to 7.5 ppm. -7.5. A data is given. Then third one, if metal equal to iron and delta hydrogen equal to -6.8 ppm. A data is given in the question paper. Option D, metal equal to cobalt and delta hydrogen equal to -6.8 ppm. Choose an appropriate option. Since it satisfies 18 electron rule, 4 carbon monoxide 8 electron count, 2 hydrogen 2 electron count, 8 plus 2 10. So definitely metal must be an 8 electron donor. 8 electron donor means 8th group element. 8th group element may be iron. So option A or C. From A or C, which one is correct answer? Since this is a metal carbonyl hydride, definitely the delta value must be negative. Here delta value is positive. Here delta value is negative. So definitely option C will be the right answer. Okay, so that is about the H1 NMR spectral detail of metal carbonyl hydride. Higher the shielding, higher the negative delta value. Then number of IR bands for metal carbonyl. Number of IR bands for metal carbonyl. Please listen. In this topic, for a competitive exam, you have to memorize many data. Then only you can qualify that exam. Okay, here number of IR bands you have to memorize for a carbonyl. It's a number of IR band, whether it is 2 IR band or 3 IR band. Only method you have to memorize. Explaining why 2 IR band, why 3 IR band, that is very time consuming. For that you have to know the geometry of the molecule, the point group of the molecule, the symmetry of the molecule, then only explaining with the actual reasons. Okay, so I will give you some hints. 2 carbon monoxide, 2 CO ligands can be arranged, 2 CO ligands can be arranged in 2 ways. 2 carbon monoxide ligands can be arranged in 2 ways. This is metal, first carbon monoxide, second carbon monoxide. This is called linear arrangement. This is called linear arrangement. Second method, this is the metal. Here a carbon monoxide, here another carbon monoxide. This is called bend arrangement. So if 2 carbon monoxide ligands connected to metal, it may be linear or bent. Okay. Then the IR band, number of IR band, you know the basic principle of IR spectroscopy, which is due to the change in dipole moment. Change in dipole moment, if a molecule having change in dipole moment, then only that is IR active. So here this molecule symmetric stretching is there, asymmetric stretching is there. MCO linear, symmetric stretching means both metal carbon bond are stretching equally. So that will not cause any change in dipole moment. So the symmetric stretching, in linear symmetric stretching, IR inactive. Symmetric stretching is IR inactive. Why? If you are stretching this metal carbon bond and this metal carbon bond symmetrically, then that will not produce any change in dipole moment, and symmetric stretching for a linear metal carbonyl is IR inactive. IR inactive. At the same time, if one metal carbon bond is stretched, then other is compressed. So that is an asymmetrical type of stretching. Asymmetrical type of stretching, both the bond lengths are different. So asymmetrical stretching is IR active. Asymmetrical, all these are the information you studied in the MSc classes. So in the case of linear metal carbonyl, 2 types of stretching, bond stretching is there, symmetrical stretching and asymmetrical stretching. Only symmetrical stretching is IR only asymmetrical stretching is IR active. What is the reason? Symmetrical stretching will not produce any change in dipole moment of metal carbonyl bond, so it is inactive. Only asymmetrical stretching active. So my question, what is the number of IR band for linear metal carbonyl? For linear arrangement, only 1 band. For linear arrangement, only 1 band. Then what about bend carbonyl? In bend carbonyl, symmetric as well as asymmetric, both are IR active. Symmetric stretching, IR active, as well as asymmetric stretching, that is also IR active. So what is the total number of band for bend carbonyl? For bend carbonyl, 2. You have to memorize this thing. For linear carbonyl, only 1 band. For bend carbonyl, 2 band. Okay. Once again, two CO ligands can be arranged in 2 ways. First one in a linear fashion, second one bend fashion. In linear fashion, symmetrical stretching inactive, only asymmetrical active. In bent fashion, both the symmetrical and asymmetrical stretchings are IR active. Okay, then what is the total number of IR band? For linear only 1, but 1 for asymmetrical. For bend symmetrical as well as asymmetrical active, so bend 2 IR band. Okay, for linear, number of IR band equal to 1. For bend, number of IR band equal to 2. Then we can start our section. Number of IR band for metal carbonyl. In this section, we have to discuss the number of IR band for tetrahedral geometry, TBP geometry, and octahedral geometry. Okay, so first one, number of IR band for tetrahedral geometry, TD geometry. Best way you have to memorize what is the number of IR band. Okay, so in TD geometry 4 cases are there. First one, MCO 4 times, 1 metal and 4 carbon monoxide. Tetrahedral arrangement, CO, 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 1 metal and 4 carbon monoxide. This is highly symmetric. A tetrahedral geometry is highly symmetric geometry. Okay, so M, CO, 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 all corners are equivalent. If the geometry is highly symmetrical, number of IR band equal to 1. Number of IR band equal to 1. So what is the number of IR band for a complex of the type MCO4, tetrahedral MCO4? Only 1 IR band. Only 1 IR band. Okay. Next one. 1 carbon monoxide replaced by another ligand. MCO thrice L. 1 carbon monoxide replaced by another ligand. Then it becomes metal, ligand, carbon monoxide, carbon monoxide, carbon monoxide. Okay, carbon monoxide, carbon monoxide, carbon monoxide. What is the number of IR bands? This is not at all symmetrical. This is symmetrical, but this is not symmetrical. Here, 1 metal is there, 1 metal here, 3 carbon monoxide on the 3 corner of a pyramid. So all are bend. This is bend. This will be also bend. So 3 bend metal carbonyls are there. CO, metal, CO. CO, metal, CO. CO, metal, CO. All are bend. All are bend carbonyl. What is the number of all are equivalent? All are equivalent. So what is the number of IR band for bend carbonyl? 2. 2. Why 2? Why 2? Because MCO, MCO. Here bend carbonyl is present. So both the symmetrical as well as asymmetrical stretching are IR active. So definitely 2 IR. So a complex MCO4 1 band, MCO3L 2 band. Then third case. Third case, M2 carbon monoxide replaced by 2 other ligand, MCO2L2. How you can represent? Metal, tetrahedral geometry, here ligand, carbon monoxide, carbon monoxide. How many bands? CO, MCO, bend geometry. For bend geometry, number of IR band equal to 2. Both the symmetrical as well as asymmetrical stretching is IR active. Okay. Then last case, MCO L3. MCO L3. 3 carbon monoxide replaced by 3 other ligand. Okay. MCO L3. Okay. All monocarbonyl irrespective of the geometry. Monocarbonyl means In a complex, only one carbon monoxide is present. Okay, in a complex, only one carbon monoxide is present. All monocarbonyl, irrespective of the geometry, whether tetrahedral or TBP or octahedral, or in a complex there is only one carbon monoxide present, then it will have only one IR band. One IR band. So that's all. That's the 4 cases of tetrahedral geometry: MCO4, MCO thrice L, MCO twice L2, MCO L3. MCO4 is highly symmetric. If symmetric, only one band. For symmetric, only one band. Then next one, MCO thrice L, bend 2. Then next one also bend 2. Then all monocarbonyl, irrespective of the geometry, only one. Then TBP geometry. TBP geometry, trigonal bipyramidal. In tetrahedral 4 cases are there. In TBP total 5 cases are there. Okay, first one MCO5, 1 metal and 5 carbon monoxide. 1 metal and 5 carbon monoxide. Okay, so what will be the arrangement? In TBP, this is the trigonal plane. This is the trigonal plane. Metal at the center. Metal at the center. Here a carbon monoxide. Here a carbon monoxide. Here a carbon monoxide. This is called equatorial position. Equatorial position is a plane. A triangular plane is the equatorial position. Okay. Then one above and one below. Above a carbon monoxide, below a carbon monoxide. Okay. The axial bond length is little bit longer. You know, in TBP geometry, the bond length at the axial position is longer than equatorial bond length. Okay. So this is not a symmetrical geometry. Why it is not symmetrical? Symmetrical means all the bond length, bond angles all are equivalent. Bond length and bond angles are equivalent. Here axial bond length is 90, equatorial axial bond angle is 90, equatorial bond angle is 120. Axial bond length longer. So it is not symmetrical. If it is a symmetrical, then only one signal will be there. This is not symmetrical, but the trigonal plane is symmetrical. This is the trigonal plane. That trigonal plane is symmetrical. This axial is also symmetrical. So one band for the symmetrical plane and one for the axial linear carbonyl. So total number of IR band equal to 2. For more explanation, you have to know, you have a detailed knowledge about the point group, symmetry elements, other thing. This is the simple explanation. The trigonal plane is symmetrical. 1 metal and 3 carbon monoxide, all are equivalent. Then 1 for the linear. So total 1 symmetrical plus 1 axial and 1 equatorial. So total number of IR band equal to 2. Then what will be the next case? 1 carbon monoxide replaced by another ligand. 1 carbon monoxide replaced by another ligand. Okay, MCO4 times L. MCO4 times L. What will be the geometry? This is the trigonal plane. Here metal is present. Here 3 corners, 1 above, 1 below. Okay, the new ligand L can be present in axial position. Then all 4 carbon monoxide at other position. One more possibility is there. This is the trigonal plane. This is metal, 5 corner. Okay. If the carbon monoxide is present at the equatorial position, then newly added ligand present at the equatorial position, then all carbon monoxide at other site. So these are the 2 possible arrangements of MCO4L, 4 carbon monoxide and 1 another ligand. Okay. Here the other ligand L at axial position, here other ligand at L at equatorial position. All 3 equatorial positions are identical and equivalent position. Okay. Then how many how many signals are for this one? Please give me an answer. How many IR band? Number of IR band. Number of. Please listen. Here this trigonal plane is symmetrical. CO, CO, CO. Trigonal plane is symmetrical. For symmetrical, one signal. Plus this is a bench. COM, CO. COM, CO is a bench. So total how many? Total how many? Plane symmetrical 1 plus 1 bench. Total 3 IR band. Total IR band equal to 3. Okay. You have two options. Just memorize MCO4L equal to 3 band or give a logic. Okay. From my opinion, just memorize MCO5 total 2 signal, MCO4L total 3 signal. That's the best method for a competitive exam. Okay. Then here, what about how many signal? Here this is a bench. Here 2 bends are there. This is a bench. CO, M, CO. Then here also CO, M, CO. So it is considered as, for more explanation, point group is needed. This is considered as 2 bend ligand and total IR band equal to 4. Total IR band equal to 4. Considered as 2 bend ligand. Okay. So total IR band equal to 4. Okay. Then next one. Third one. MCO thrice L2. 2 carbon monoxide replaced by 2 other ligands. What are the possible geometries? What are the possible geometry? 2 other ligands are there. 2 other ligands are there. Sketch the possible geometries. Sketch the possible geometry. First one, 2 L ligand in axial position. 2 L ligand in axial position. This is a triangle. The 2 L ligands in axial position. Here carbon monoxide, carbon monoxide, carbon monoxide. Then next case, a triangle, metal at the center. Okay. 2 L ligands in equatorial position. Here carbon monoxide, carbon monoxide, carbon monoxide. Third possibility, one L in axial position, one L in axial position and the other L in equatorial position. Then here CO, CO, CO. Okay. So find the number of IR band. LL, the plane is symmetrical. Plane is symmetrical. If plane is symmetrical, only 1 IR band. Plane is symmetrical. Symmetrical, only 1 IR band. What about this one? What about this one? 2 L ligands in equatorial position. How many IR band? How many IR band? Total number of IR band. This can be considered as a linear and 1 bend, total 3. If 2 L ligands are equatorial, here both axial, here both equatorial. In both equatorial, MCO, that bond length is little bit longer. So this is a linear and 2 equivalent bend. So total 3. Total 3. Here also total 3. So that is our third case. That is our third case, MCO thrice L2. MCO thrice L2. More explanation, very time consuming. 1, 3, 3. Okay. The next one. What is the next case? Next case. One carbon monoxide replaced by another ligand. MCO twice L3. MCO twice L3. Previous year question of CSIR net exam. MCO twice L3. A triangle, metal at the center, 5 corner. One more possibility, a triangle, metal at the center, 5 corner. Okay. Then CO twice, that CO and CO may be trans. Carbon monoxide and carbon monoxide trans. Then ligand. Then another possibility, CO and CO are cis to each other. Then ligand. So these are the two possibilities. Carbon monoxide and carbon monoxide trans in the axial position. Then here carbon monoxide and carbon monoxide cis. So when they are trans to each other, this is a linear CO1. Linear CO, only one IR band. This is COMCO, bench. For bench, 2 IR band. For bench, 2 IR band. Okay. So for linear, 1, and for bench 2. Or you can say that for trans, 1 for trans and 2 for cis. 2 for cis. Okay. 2 for cis. Cis means always the cis arrangement is a bend arrangement. Linear arrangement is a trans arrangement. So for trans, MCO twice L3, 1, and for cis, MCO twice L3, 2. Okay. The last one. Last and fifth one. Fifth one. MCOL4. You know, all monocarbonyl, that means only one carbon monoxide, irrespective of the geometry, only one IR band. Only one IR band. So that's all about the 5 cases of TBP geometry. MCO5, MCO4L, 2 cases, MCO3L2, 3 cases, MCO twice L3, 2 cases, then here only 1 cases, only 1 IR band. Then third case, octahedral. Here 6 cases are there. Octahedral. Please listen. First one, MCO6. 1 metal and 6 carbonyl. Octahedral can be represented as this fashion. The peculiarity of octahedral is highly symmetrical. Highly symmetrical means all the bond length are equivalent, all the bond angles are equivalent. Axial as well as equatorial bond angles are 90 degree, all bond length equivalent. So octahedral is highly symmetric. Okay, for symmetric, number of IR band equal to 1. Only 1 IR band. Note it. For any symmetrical arrangement, only 1 IR band. Next one, MCO5 times L. 1 carbon monoxide replaced by other ligand. What is the arrangement? COL. Only one possibility. The CO in axial or equatorial identical, because all 6 positions are equivalent and identical. Okay, in octahedral, due to high symmetry, axial as well as equatorial positions are identical. So this L may be in axial or equatorial, both are equivalent. So how many signals are there? MCO5L. This is the square plane. 1 metal and 4 carbon monoxide. Square plane is symmetrical. Now one L ligand is attached here. It's a symmetry loss. Then the square plane is symmetrical. Then one COMCO bend. For symmetrical square plane, one bench, then CO, a bench, total 3 bench. Total number of bench equal to 3. This bench and this bench are equivalent bench, so it is treated as 1. Okay, so total 3 bench, 3 IR bench. Then what will be the next case? 2 carbon monoxide replaced by 2 ligand. Total number of IR bench. Third one, MCO4L2. MCO4, 2 carbon monoxide replaced by 2L. What are the possible arrangement? This is the square plane, metal, in first case L and L cis. L and L are arranged in cis manner. This is L and L. Here CO, 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 CO. L and L are cis. Then in the next case, metal, L and L are trans. Then in remaining positions, carbon monoxide. Remaining position, carbon monoxide. How many signals? This is the cis arrangement and this will be the trans arrangement. What is the number of signal for this trans arrangement? L and L are trans, square plane is symmetrical, so only one IR band. Only one IR. Then this is not at all symmetrical. Here CO is a bench, CO is a bench, so it can be treated as 2 bench. 2 bench means 4 signal. 2 bench means 4. So MCO4L2 cis 4. In cis treated as 2 bench and trans square plane is symmetrical, so only one IR band. Okay, then fourth case. Fourth case. You can memorize this number of IR band with some your logic. Then MCO thrice L3. In coordination chemistry, you studied in isomerism. Okay, in isomerism section, you studied that a complex of the type MCO thrice L3 exhibit a special type of isomerism called Mer and Fak isomerism. Mer and Fak isomerism. A complex of the type MCO thrice L3. If this formula, that will exhibit a special type of isomerism called Mer and Fak isomerism. Mer means meridian, and F means facial. F means facial. Okay, Mer, Fak, meridian and facial. So what is Mer isomer? Then what is the arrangement in Fak isomer? Please listen. This is an octahedral. A square plane is there. This is the square plane. A metal will be at the center. The 4 corners of the square, 2 axial position, all are equivalent position. Then another one, a square, metal at the center, 4 corners of the square and the 2 axial position. Okay. Meridian means a meridian can be generated in the square plane. This is the square plane. Consider 3 corners of the square plane. Then draw a line. This is a meridian. You know the meaning of meridian. Metal at the center. And this is a meridian. Meridian means exact half of the a 3 corners connecting the square plane. That is called a meridian. At the meridian position, same ligands occupy CO, CO and CO. 3 CO are occupying the meridian position. Then other ligands on other position. This isomer is called Mer isomer. This isomer is called Mer isomer. That means same ligands occupying same ligands occupying the three corners of square plane. Same ligands occupying the three corners of square plane. This is a mer isomer, meridian. Then FAC means if you complete this octahedral, this is an octahedral, and in this octahedral this is a triangular face. This is a triangular face. Okay, please listen, this is a triangular face. Is it? If identical ligands occupying this triangle, any of this triangular face. Okay, so a facial means two corner of square plane and one axial plane. It joins to form a facial. Okay, three corners of square plane joins to form mer, and two corner of square plane and one axial position join to form the face, facial or FAC isomer. Then how you can distinguish a mer isomer and FAC isomer? In a mer isomer, identical ligands at the three corners of square plane. In a FAC isomer, identical ligands at the two corners of square plane and one axial plane. This is a face of octahedral. This is a meridian of octahedral. So it's a mer isomer, and this is FAC isomer. Then for mer 3 IR band, and for FAC 2 IR band. Memorize, for mer number of IR band equal to 3, and for FAC number of IR band equal to 2. That is our question. For FAC 2, for mer 3. Okay, mer and FAC isomers exhibited by MCO thrice L3 type complex. In exam hall, our confusion, mer 3 or FAC 2, 3 or 2, that is in our mind. Mer 3 or FAC 2 or FAC 3 or mer 2, that's our confusion. For that, in alphabetical order, F, then only M. M is a higher alphabet. This is F, this is M. A, B, C, D, F. M is a higher alphabet. For higher alphabet, higher value. So for FAC, only 2. For mer, 3. M is a higher alphabet, so higher number, 3. FAC, F, 2. Okay, you can remember that. Okay, so that is the IR bands for mer and FAC isomer exhibited by MCO thrice L3. Okay, the next one. What will be the next case? MCO twice L4. I think fifth case. Sketch the possible geometries of MCO twice L4. What are the possible geometry? A square plane, metal at the center, 6 corners. Then a square plane. Two possibilities are there. M. First possibility, CO and CO trans. CO trans, then L. This is called trans arrangement. Next one, CO and CO cis, then L. Here axial equatorial comparison is not there because axial and equatorial all are equivalent. Okay, so find the number of signals. First case, linear. For linear MCO 1, this is bend. For bend it is 2. Is it? This is linear. For MCO linear, CO MCO bend. For bend it is 2. Okay, then last case. Sixth one, MCO L5, you know, all monocarbonyl, irrespective of the geometry, only one IR band. So that's all about the different case. For tetrahedral 4 cases, for TBP 5 cases, for octahedral 6 cases. Okay, number of IR band. Some of them are confusing. Confusion is you didn't know the point group or symmetry elements of that molecule, that we will study later. So based on this, CSIR asked questions 3 or 4 times. Some of the previous questions that we are going to discuss. Then write a previous year question. New CO4 FeCO twice PPH3 thrice. FeCO twice PPH3 thrice. So this is a TBP molecule. Okay, is 1892 centimeter inverse at room temperature, RT means room temperature. Predict its structure. A complex FeCO twice PPH3 thrice is 1892 centimeter inverse at room temperature. Predict its structure. So a TBP molecule, what are the possible arrangements? MCO twice L3, that is the type. Iron, the 6 corners of TBP, iron. Okay, then CO twice, that may be trans arrangement or cis arrangement. Trans arrangement or cis arrangement. Then the other ligands L, here L. Okay. So in question, new CO4 FeCO twice PPH3 thrice is 1892 centimeter inverse, means only one band is there. Only one value is there. One value means only one band at 1892 centimeter inverse. For this complex, only one band at 1892 centimeter inverse. For cis or trans, one band. For trans linear arrangement, one band. For cis bend arrangement, 2 band. So which one is the right answer? So definitely this will be a trans complex. One band means trans complex, 2 band means cis complex. So this type of question that you can expect, a complex of this type having only one band means definitely arrangement is for trans linear arrangement, one band. For cis bend arrangement, 2 band. Okay. Then write the next question. Differentiate cis and trans. Differentiate cis and trans. CO twice PF3 4 times. CO twice PF3 4 times using IR. Differentiate cis and trans using IR. This is an octahedral complex. Chromium at the center, 6 equivalent position. Here also chromium at the center, 6 equivalent position. Okay. Cis means both carbon monoxide at adjacent position. Trans means both carbon monoxide at opposite position. So cis and trans. Okay. Then here L. Now you can predict the number of IR band. Here it is bend. Cis means bend. So 2 IR band. and trans means linear, only one IR band. For cis, 2 IR band, trans, 1 IR band. So you can differentiate based on the number of IR. So it's a very important topic. You can expect a question from organometallic chemistry. So we completed the section metal carbonyls. Metal carbonyl, bonding, IR stretching frequency, synthesis, reactions, acidic basic strength, H1NMR spectral detail as well as number of IR bands. So metal carbonyl topic is completed. In next lecture we will discuss about carbene and carbine.